Hello everyone, I'm very happy to present our work. Randomized lasso caches are still vulnerable to cat side channel attacks, but we can fix it. This is joint research between the Institute of Information Engineering at CES and Pennsylvania State University. I'm Wei Song, the first author of this paper. Randomized caches have recently been revived as a promising defense technique against company-based cat side channel attacks, targeting the last level caches. Two of the latest papers, CGS and Scattercache, published at nearly the same time. They both use randomized skewed caches to thwart the remaining attacks against the randomized set cell-shaped caches. However, after detailed analysis, a number of issues have been discovered. The possibility of using flash instructions to directly flash the evasion set has been overlooked. The possibility of using smaller evasion sets with lower evasion rate has been overlooked as well. Meanwhile, we found that counting the remap period by the number of LLC accesses is flawed. As hardware designers on the defense side, we actually believe that randomized caches is the proper defense that should be adopted. We just need to fix the problems. For this end, we propose several ideas in this presentation. We need to count remap period by LLC evictions and further reduce remap period. Using multi-step relocation can reduce the cost in each remap. Instead of periodically remaps, trigger remaps when under attack might be a good idea. Also, we are in favor of the non-skewed set cell-shift caches rather than the skewed ones. Let's first recall the structure of randomized skew caches. Here shows a randomized skew cache with 4 ways divided into 2 skew partitions. The mapping from the addresses to cat set indexes is encrypted, so that attackers cannot form evasion sets by aligning addresses. They are forced to search for evasion sets at runtime. To further increase the difficulties in searching for evasion sets, the keys used in each skew partition is different, and the address might be cached in any skew partition with equal chance. As a result, it is becoming nearly impossible to find evasion set using fully concurrent addresses within any reasonable period of time. Unfortunately, attackers might instead choose to use partially concurrent addresses. Although the found evasion sets are larger, they're still useful. As shown in the figure, when the evasion set contains enough partially concurrent addresses, eventually the cached victim data will be dislodged by one of them. Currently, there are 3 types of searching algorithms that still work on randomized cache. The first one is called group elimination, which we call GE in this presentation. It starts with a large evasion set and then pruning it by removing multiple addresses at a time to speed up the process. The second one we call conflict testing, CT for short. In this algorithm, the attacker constantly accesses random addresses and tests each one of them to see whether it is conflict with the target. If so, it is then put into the evasion set. The process stops when enough conflict addresses are found. The final one is called prime, prune, then test in this paper, or PPT for short. It starts with a really large prime set to prime the whole LLC. Then the prime set is pruned to make sure all remaining addresses are concurrently cached. Finally, it tests the complete addresses in the prime set by traversing the set again after revisiting the target. Generally speaking, all algorithms are pretty efficient and finish in linear time. The GE algorithm is robust, but does not work in randomized skew caches. The ALC trace of the CT algorithm is almost noise, but it incurs a huge amount of accesses to the victim. The PPT algorithm has a minimal number of victim accesses in the 3, but it is most sensitive one regarding to the replacement policy used by the cache. Now let's talk about the problems found in this paper. One known issue with using evasion sets composed of partially concurrent addresses is the reusability. Let's show an example. Assume the evasion set has dislodged the victim data the first time, and we try to use it again. The victim data is revisited, and it might evict one and only one address of the previously used evasion set. Since all other addresses in the set might have already been cached, and evicted one is only a partially concurrent address, reusing the evasion set has only a 50% chance to dislodge the victim data again. If that fails, the evasion set becomes useless. To resolve this problem, The existing solution is to use a prime set to prime the whole LLC, which also evicts the eviction set as well, although priming the LLC is a rather slow process and causes enormous amount of noise. So we thought, why not just flash the eviction set directly? No one says attackers cannot use the CL flash instruction if it is available. Because the eviction set belongs to the attacker, they can be flashed by the attacker. By doing this, we can save a huge amount of LLC accesses and significantly reduce time and noise. The analysis provided in the original work of PPT is then over pessimistic. The authors of the scatter cache argues attackers are likely to use eviction sets with 100% eviction rate. This means the eviction sets are large and attackers need to spend quite a long time to find them. As shown in our estimation, 39 partially congruent addresses are required to achieve an 80% eviction rate, while only 25 addresses are needed for achieving a lower 30% eviction rate. Since the time cost in finding eviction set is linear with the size, using larger eviction sets reduces the chances to launch a successful attack. If I were the attacker, I would think, why not use smaller eviction sets with a reduced eviction rate? Some attacks might just work with these small eviction sets. Two papers published recently have already agreed with this on this. We further argue that, at least in the evict plus time attacks, attackers can achieve 100% eviction rate by just applying the same small eviction set multiple times, as shown in the figure. The overall time is significantly shorter than finding and then applying a larger set. Proposed by CCF, periodical remap can efficiently support the search for efficient set at runtime. They also estimate that remap every 100 LLC accesses per cache block is frequently enough. However, they seem to use the cache accesses rather than LLC accesses in the estimation, which fail to consider the filter effects of the L1 caches. As a result shown in the figure, when using the CT algorithm, the number of the LLC accesses is equivalent to the number of evictions, and are only half of the total cache accesses. This is because almost all accesses to the victim data are served by the L1 cache alone. The period estimation in CCS is wrong, and we propose to count the remap period by LLC evictions rather than LLC accesses. According to our experiment, GE does not work on randomized skew caches. CT incurs lower LLC evictions than the PPT algorithm, therefore the remap period should be estimated targeting the CT algorithm. Using the same method used by CISA, these slides reveal the relationship between the remap period and average time needed to find a small eviction set with the 30% eviction rate, with different numbers of skew partitions. If we consider 1 year as a secure enough target, the non-skewed CISA needs to be remapped every 10 evictions per cache block. And even for the 16 skewed cache, the remap period is only 39. The benefit from using extreme skewing is marginal. Then comes the question. The estimated remap period is similarly much shorter than the 100 accesses per cache block preferred by CISA. Is this a problem? Well, it may not be. So we put it into a comparison using the SPEC CPU 2006 benchmark. ACC10 refers to the remap every 10 accesses per cache block, while EV10 means remap every 10 evictions per cache block. The overhead in terms of missing rate caused by remapping is reduced by 87% if we count remap period using LLC evictions. The overall overhead is marginal 0.077% compared with no remap. The underlying reason here is normal applications run at much lower miss rate than attackers. So the remap frequency for normal applications is much lower, so does the performance overhead. Here shows a more detailed comparison between the two. This is a trace of the runtime miss rate extracted from running the 403 GCC benchmark case. In each trace, a vertical pink line indicates a remap. Note that the upper one is actually remapping every 100 accesses per block rather than 10. But we already see the differences between the two. Now let's look at the period inside the red circles. When miss rate is low, the remap triggered by the remapping by evictions is significantly less than remap by accesses, which indicates lower performance overhead when the LLC is efficiently used. While for the period in the blue circle, where the miss rate is high, remap by evictions does trigger more remaps. But the original cache performance with high miss rate is rarely suffered. More remaps during this period only marginally reduced already low performance, not much of a problem. To further reduce the cost involved in the remap, we propose to use a multi-step relocation scheme instead of the one-step relocation used in CISA. According to our estimation, 40 to 50% of the cache blocks are evicted in CISA every time there's a remap. When multi-step relocation is used, the remapping process will keep trying to relocate a cache block until a free location is found or a previously relocated block is evicted instead. Using multi-step relocation does not prolong the remap process, and introduced overhead is just a retrial. Using a new encryption key when using the old one results in miss during the remapping process. Considering remap is still an infrequent event, this cost, in both latency and hardware, is trivial. Finally, we propose to trigger extra remaps using attack detection. Instead of using randomized skill caches, we actually prefer and promote the adoption of non-skilled randomized set-associated caches, such as CISA. Skilled cache might bring some performance benefits, but in reality, acquiring multiple cache sets with different cache set indices can substantially reduce the available bandwidth of the LLCs through concurrent transactions, or significantly increase the hardware complexity and prolong LLC's latency. We guess this is one of the reasons why skill caches have not been widely utilized in nowadays processes, considering the claimed performance benefit. However, for randomized set-associated cache, periodical remap stops only the CTLs. Both GE and PPT becomes viable again. Luckily, both algorithms incur abnormally high amount of efficiency on the target cache set, which can be easily detected using a hardware detector. This slide shows the detection result for two PPT attacks. The hardware detector analyzed the distribution of cache events over the cache set. As shown on the left-hand side, the distribution of the cache access and evictions looks like noise. But if we apply a Z-score standardization on them, as shown on the right-hand side, two peaks clearly appear on the distribution of the cache evictions. This is because multiple evictions are triggered inside the target cache set during the final test phase of the PPT algorithm. Similar peaks appear for the GE attack as well. When the large eviction set is effectively prone to a small one, cache evictions triggered by the traversing eviction set naturally converge to the target set, so comes the highly unbalanced distribution caused by the Z-score standardization. Alright, now let's have a look at the overall performance. Graph on the left shows the number of remaps triggered by periodic remap and attack detection. It shows that applying attack detection leads to 26% extra remaps, but this cost can be efficiently alleviated by the multi-step relocation. As shown on the right-hand side graph, when all techniques are applied to a non-skilled CISA, the overhead in miss rate is a tiny 0.007%. On the contrary, when the maximum skill is applied, the overhead increased to 1.5 more misses. It is shown that randomized set-associated cache can be made secure enough with marginal performance cost, while using extreme skewing actually hurts the performance. Okay, so 4 ideas are proposed in this paper. Remap by counting LLC evictions. Use multi-step relocation to reduce remap cost. Trigger remaps by attack detection, and promote the use of non-skewed set-associated caches. For more details, please read our paper. Thank you for your listening.